On March 10, 2016, a computer placed a black stone on a Go board in Seoul. Move 37 looked wrong. Professional commentators paused.
Ooh.
That's a very surprising move.
I thought it was a mistake.
I thought it was a quick miss, but
A clicko. And if we were online Go, we call it a clicko.
Lee Sedol, one of the greatest Go players alive, left the room to think.
Lee has left the room.
He left the room after
He left
that.
the room after that move.
The machine had selected a move so unusual that, according to DeepMind, a human professional might play it once in 10,000 attempts. It was not a glitch. It was the beginning of a new strategy. AlphaGo won that game and eventually defeated Lee Sedol 4-1. More than 200 million people watched the series. In much of the West, it was treated as another impressive technology demonstration. In China, it landed more like an alarm clock the size of a building. Humanity had apparently spent 2,500 years playing Go, only for the game to become industrial policy. 1 year later, China's State Council published a national development plan covering research, chips, robotics, manufacturing, and public services, with the goal of making China a leading global center for artificial intelligence by 2030. Then came the contradiction. The United States controlled the most important AI chip designs. American export rules restricted China's access to advanced processors and the equipment required to manufacture them. US companies had more private investment, more frontier models, and far greater access to advanced data center infrastructure. China was supposed to fall behind. Instead, Stanford's 2026 AI Index reported that the performance gap between the best American and Chinese models had effectively closed. As of March 2026, the leading American model was ahead by only 2.7%, and models from both countries had repeatedly traded places near the top. So our investigation begins with one question. How did a country blocked from the world's best AI hardware get this close, this quickly? To solve it, we need 4 visible principles: shock, choke points, efficiency, and distribution, before reaching the deeper principle connecting all 4. And that 5th one changes what the AI race is actually about. If you enjoy business and technology stories, a like and subscription helps this channel reach more people who enjoy investigating expensive problems created by very intelligent adults. AlphaGo did not create China's AI industry. Chinese universities, internet companies, and government laboratories were already studying machine learning. What AlphaGo created was urgency. The match transformed an abstract technological competition into a public demonstration. A British-built system, DeepMind, later owned by Google, had defeated an Asian champion at a game deeply rooted in Chinese history for 2,500 years. That symbolism mattered.
정말 생각도 못했어. 정말 믿을 수가 없었어. 믿을 수가 없어서 이거는 진짜. 예, 감사합니다. 한 판을 이겼는데 이렇게 축하를 받아본 건 또 처음인 것 같습니다. 이렇게 3연패를 당하고 1승을 하니까 이렇게 기쁠 수가 없습니다.
China's 2017 development plan described artificial intelligence as a new engine of economic growth. It established goals related to fundamental research, intelligent manufacturing, medical technology, robotics, autonomous systems, and semiconductor development. It was not simply a plan to build a Chinese chatbot. It was closer to reorganize large parts of the economy before somebody else does. Governments are frequently accused of moving slowly. In this case, a board game produced a national strategy faster than many offices can approve, a replacement printer. The first principle, hence, is shock. Major technological shifts are rarely driven by calm appreciation. They accelerate when a country, company, or industry suddenly sees what losing could look like. The Soviet launch of Sputnik forced the United States to rethink its space program. The arrival of the iPhone,
and we are calling it iPhone,
forced nearly every mobile phone manufacturer to reconsider what a phone actually was. And AlphaGo forced China to treat artificial intelligence as something more urgent than an interesting research project. For the United States, its own shock would arrive later. Not from a board game, but from a free Chinese AI application, suddenly appearing on millions of phones. Before that happened, Washington tried to control the part of artificial intelligence that software cannot politely negotiate with: physics. Modern AI looks like software, but it begins inside factories. Training a large AI model requires enormous amounts of computation. That computation is supplied by accelerators, such as NVIDIA GPUs, which are primarily manufactured by specialized semiconductor foundries led by Taiwan's TSMC. The wider production chain also depends on lithography, deposition, inspection, memory and packaging technologies spread across the United States, Taiwan, the Netherlands, Japan, and South Korea. This is often described as the AI stack. At the top are the applications people actually use: chatbots, design tools, coding assistants, and video generators. Below those applications sit the foundation models. Underneath the models are data centers, networking equipment, and electricity, and at the bottom are the chips. Silicon does not care about national ambition. It cares about voltage, and whether a microscopic transistor was manufactured correctly. Factories are stubborn like that. They rarely accept motivational speeches. The United States recognized that this supply chain contained strategic choke points. Beginning in 2022 and strengthened through later rounds, export controls targeted advanced computing chips, high bandwidth memory, and manufacturing equipment used to produce leading-edge semiconductors in China. The goal was not to ban every computer chip. China could still buy or produce many processors. The restrictions focused on hardware most useful for training very large AI systems and developing other advanced capabilities. That distinction matters. China has no chips makes an excellent headline. It is also false. China possessed older NVIDIA processors, modified export-compliant products, domestic accelerators, and hardware acquired before restrictions tightened. But Chinese laboratories faced real disadvantages: less access to cutting-edge processors, weaker networking between chips, less mature software ecosystems, and restricted access to the newest manufacturing tools. Meanwhile, the United States maintained an extraordinary infrastructure advantage. Stanford reported that America hosted more than 5,400 data centers in 2026, over 10 times the total of any other country. It also noted that TSMC fabricated almost every leading AI chip. TSMC's own 2025 annual report showed how quickly demand was growing. Its dollar-denominated revenue increased by 35.9% during the year, supported partly by strong demand for advanced computing and AI infrastructure. On paper, this hardware advantage should have widened America's lead, yet a choke point does two things. It slows the target down, but it also tells the target exactly where it is vulnerable. China could not immediately recreate the entire international semiconductor supply chain. Build another TSMC is not considered a serious project plan, despite how neatly it fits inside a PowerPoint box. So Chinese AI laboratories began adapting around the constraint. And one company turned that adaptation into a global event. When DeepSeek released the technical report for its V3 model, one number dominated the headlines. The company reported using 2.78 million NVIDIA H800 GPU hours for the model's final training run. Based on the estimated rental price of that computing power, the figure was commonly translated into approximately $5.6 million. That number requires a warning label. It did not represent the complete cost of creating DeepSeek. It excluded employee salaries, previous experiments, data preparation, hardware purchases, research infrastructure, and failed training attempts. Comparing that number directly with the complete development budget of a Western model would be like pricing a restaurant by counting only the gas used to prepare the final meal. Still, the underlying engineering achievement was real. DeepSeek V3 contained 671 billion parameters, but activated only 37 billion for each token it processed. It used an approach called mixture of experts, routing each task through a limited section of the model instead of activating the entire digital brain whenever somebody asked it to make an email sound more professional. Think of a traditional dense model as a company where every employee attends every meeting, accounting is present for graphic design, legal has joined the lunch order, the entire engineering department is discussing the office coffee machine. Mixture of experts sends the task only to the departments that might actually help. DeepSeek also used multi-head latent attention, which reduced the memory required to process longer conversations. It employed lower precision computation and communication techniques designed around a cluster of 2048 NVIDIA H800 GPUs. The processors did not become faster because the engineers believed in themselves. The system was redesigned to waste less of what those processors could already do. None of these concepts appeared from another dimension. Mixture of experts, reinforcement learning, and low precision training were already being developed across the global AI industry. DeepSeek's advantage was its aggressive combination of them. Its engineers treated computation as a scarce resource rather than a subscription that could simply be upgraded after lunch. DeepSeek R1 extended that philosophy into reasoning. Its experimental R10 model used reinforcement learning to develop problem-solving behaviors without first learning from human-written reasoning examples. The system began demonstrating self-checking and strategy adjustment. It also suffered from poor readability and occasionally mixed languages, proving that even an artificial genius can sound like a group chat at 3 in the morning. DeepSeek addressed those problems using initial training examples, supervised fine-tuning, and additional reinforcement learning. The company's research was later published in Nature, providing stronger independent scrutiny of its claims. This was not proof that chips had stopped mattering. DeepSeek still depended on NVIDIA hardware. Training frontier systems remains expensive, and operating reasoning models for millions of users can require even more computation than training them. The lesson was narrower and more disruptive. Better engineering could convert restricted hardware into competitive performance. Scarcity did not eliminate the need for computation. It increased the value of every available unit. That is the third principle, efficiency. And it created an uncomfortable question for Silicon Valley. If a competitor can approach frontier performance with fewer resources and offer the result at a much lower price, what exactly are hundreds of billions of dollars in AI infrastructure buying? The answer may still be quite a lot. Cheaper computation often increases total demand. When AI costs fall, more companies use it, developers attempt more ambitious products, and users generate more requests. But efficiency alone does not explain China's momentum. A brilliant model hidden inside a research laboratory has the commercial impact of a very sophisticated spreadsheet nobody opens. It still needs distribution. DeepSeek's most consequential decision may not have been architectural, it was strategic. The company released model weights that developers could download, modify, and deploy. These systems are frequently called open source models. Technically, open weight is often more accurate because their complete training data, code, and development process may not be disclosed. Still, releasing the weights changes the economics. A startup can operate the model on its own infrastructure. A university can study it. A cloud provider can host it. An enterprise can adapt it for a specialized workflow without sending every document to an external platform. The model laboratory gives up some control, but the technology spreads much faster. Everyone relaxes. Except perhaps the accountant responsible for the computing bill. By 2026, Stanford reported that American and Chinese models had traded the performance lead several times. The United States still produced more notable systems, 59 during 2025 compared with China's 35, and retained major advantages in private investment, advanced infrastructure, and high-impact patents. China's strategy was not to pretend those advantages had disappeared. It was to make capable models cheaper and easier to distribute. Then companies such as ByteDance attacked the application layer. ByteDance's Dubao became China's most used AI chatbot. Data reported by QuestMobile placed it at approximately 155 million weekly active users in late 2025. In February 2026, ByteDance released Sedence 2.0, a multimodal system capable of processing text, images, audio, and video. Reuters reported that the model quickly went viral and attracted attention for producing cinematic sequences from a small number of prompts. ByteDance described Sedence as a unified audio-video generation system designed for uses including advertising, filmmaking, and e-commerce. Its exact training dataset, however, has not been publicly disclosed. That is important, because there is a very tempting story here. ByteDance owns enormous platforms, including Douyin and TikTok. It has access to product feedback, user engagement information, and years of experience operating recommendation systems. But there is no public evidence proving that every private video uploaded to those platforms was automatically used to train Sedence. What is confirmed is that ByteDance can connect AI research, cloud infrastructure, editing software, advertising customers, and giant consumer platforms. It can release a model and place it immediately in front of creators and businesses who may use it. That is distribution with a feedback loop. China is now applying similar logic beyond consumer chatbots. Its AI Plus initiative calls for deeper AI integration across science, industrial development, consumer services, governance, and other sectors. The policy also emphasizes computing capacity, data supply, talent development, and open model ecosystems. A model becomes more economically valuable when it enters factories, logistics systems, vehicles, smartphones, robots, design software, and enterprise workflows. Benchmarks measure intelligence under controlled conditions. Deployment measures whether anyone can turn that intelligence into lower costs, quicker decisions, or useful products. Preferably before the quarterly earnings call begins asking why the AI budget now resembles the GDP of a small island. We now have 4 principles. Shock created urgency, choke points created pressure, efficiency converted pressure into engineering, distribution converted engineering into influence. But these are not 4 separate stories. They are components of one operating system. And that brings us to the 5th principle, integration. Popular version of the US-China AI race asks which country has the smartest model. That is rapidly becoming the wrong question. Models improve quickly. Benchmark gaps shrink. Open weights allow engineering techniques to travel across companies and borders. A temporary lead can disappear between 2 product launches and 1 extremely nervous board meeting. The more durable advantage is the ability to integrate the entire stack: research, semiconductors, electricity, cloud infrastructure, foundation models, software, consumer applications, factories, supply chains, policy, and talent. The United States remains extraordinarily strong at the top of the stack. It leads in advanced chip design, frontier laboratories, private investment, data centers, cloud computing, and many of the world's strongest commercial AI systems. China's strength is different. It is building a system intended to push AI horizontally across companies, consumer devices, and physical industries, while using open models and intense domestic competition to reduce prices. That does not guarantee victory. China still faces semiconductor restrictions, high energy requirements, limited transparency, censorship, privacy concerns, and unresolved legal questions surrounding intellectual property and training data. Low prices can accelerate adoption while making profit surprisingly difficult. Giving away an expensive product is excellent for market share and slightly less magical for accounting. The United States has its own contradictions. Its largest technology companies are investing enormous amounts in AI infrastructure, while investors continue asking when those investments will produce reliable returns. Power networks must support new data centers. Copyright lawsuits remain unresolved. Companies want developers to depend on their platforms while also protecting the models that make those platforms valuable. Neither country has solved the complete equation, but integration explains why restricting advanced chips did not end the race. The controls targeted one layer. China responded across several others. It improved model efficiency. It expanded domestic semiconductor alternatives. It distributed open weights. It connected AI systems to giant consumer platforms. And it made deployment part of national industrial policy. The deeper lesson is not that export controls always fail or that hardware has become irrelevant. The restrictions raise China's costs and continue to limit access to leading-edge manufacturing equipment. The lesson is that technological power rarely comes from controlling one miraculous component. It comes from connecting imperfect components faster than everyone else. 10 years after AlphaGo's Move 37, the most important move in artificial intelligence may no longer be a surprising answer generated by one model. It may be the system surrounding that model. Who can manufacture enough chips? Who can supply the electricity? Who can lower the cost of completing a useful task? Who can place AI inside real businesses without creating security, privacy, and legal chaos? And who can turn research into products before the technology changes again? The electricity grid, incidentally, does not award bonus points for winning a benchmark. The United States still holds major advantages. China has not won the AI race. There may never be a clean finish line, but the assumption that controlling the best processors would automatically control the future of AI has already been weakened. China was forced to optimize. Then it used open models, aggressive pricing, and widespread distribution to make those optimizations matter. The next phase will not be decided by one chatbot, one viral video generator, or one impressive benchmark score. It will be decided by which ecosystem can combine intelligence, infrastructure, and adoption into something reliable, affordable, and genuinely useful. That is the 5th principle. If you reach the end, comment with the principle you believe will matter most. And subscribe for more investigations into the hidden systems shaping technology, business, and the global economy.